So the aim of this video is to give you some practice studying a problem about conservative vector fields. So here we have a vector field. It has a parameter kappa in it. And the question that I ask you first is, for which value of kappa is our vector field a conservative vector field? After you've found that, then the next question is to find the scalar potential phi that corresponds to the conservative vector field with that value of kappa substituted in here. And then the final question is to use the scalar potential to find the line integral of our vector field along some path which links the point 1, 2, 3 to the point 4, 5, 6. So going from here to here. And what I'd suggest is you try to do these problems with pen and paper and then come back and you can see if you agree with the answers I have, and if you're stuck you can look at the answers. So see you in a short while. Okay, welcome back. Let's look at the answer to the first question on the next slide. So our vector field is defined in 3 dimensions, and in 3 dimensions the test for a conservative vector field is the curl of the vector field 0? In other words, is our vector field irrotational? So we're just going to work out the curl of this vector field. So we write out this determinant, and the bottom row are the elements, the coefficients of the vector field in the I, j and k directions. So let's just work them out. In the I direction, we ignore that row and that column, and we take the derivative of this with respect to y, and then we subtract the derivative of this with respect to z. So here we're going to get 2, and then we're going to subtract, and the derivative of z with respect to z of this is going to be 0 minus 0 plus kappa. So here we are going to have 2 minus kappa. In the j direction, as we go along here, we now put in a minus sign, and then we differentiate this with respect to x, so we ignore this column and this row, and the derivative of 2y with respect to x will be 0, and then we will subtract the derivative with respect to z of this, and there is no z here, so that derivative will also vanish. And then in the k direction, we ignore this row and this column, and we have the derivative with respect to x of this, and that's going to give us 1 minus 3x squared over y squared, plus, and there's no x here, so we'll get 0 from it. And then we subtract the derivative with respect to y. Remember, we're ignoring this and this. So the derivative with respect to y of this, and this is 3x squared times y to the minus 1, so we're going to get minus 3x squared times y to the minus 2, and that's this term here. And then we're going to get plus, and the derivative of this with respect to y is just 1. And what we see is that these terms all cancel. Here we have 1, here we have minus 1, here we have minus 3x squared over y squared, and here we have plus 3x squared over y squared. So those terms all cancel. So we are left, all in all, with the curl of our vector field is 2 minus kappa in the I direction. So our vector field will be conservative if kappa is equal to 2. And that is the answer to the first part of the question, and in the rest of this video I'm going to replace here kappa by 2 so that we are dealing with a conservative vector field. So what we've done on this slide of our video is we've taken the vector field, we've said we want the curl to vanish, we've calculated the curl, simplified where possible, and seen that the curl vanished if kappa was equal to 2. With that, let's go on to the second part of the question. So here is our vector field, and I've replaced kappa by 2, so we know that this vector field is conservative. The convention that I'm going to use is to say that a conservative vector field can be written as minus the gradient of phi. You may find that other people will write it as plus the gradient of phi. That is just a redefinition of phi by a minus sign. It doesn't make much difference at all. So, what do we know? Well, this component here must be minus the derivative with respect to x of phi, because we know what the gradient of phi is. It's going to be minus, open brackets, d phi dx in the I direction, plus d phi dy in the j direction, plus d phi dz in the k direction. So this here must be minus d phi dx. And I've just written that out there as an equation. So we can obtain phi, or at least some information about phi, by integrating this with respect to x. So if minus the partial derivative of phi with respect to x has this form, then if we integrate it with respect to x, we are going to obtain, well, x squared, we add 1, gives us x cubed, divide by 3, that will cancel that. So we'll have x cubed over y, that's here, plus, and then the integral of y is xy. But we've integrated this with respect to x, so there could be some arbitrary function of y and of z here. And if you were to differentiate this with respect to x, you would obtain 3x squared over y plus 0, because there is no x dependence. So what we know about phi is very useful, but it hasn't told us everything. So now we look at the second component, and we integrate that in the same way, but now with respect to y. So we'll obtain minus phi is the integral of this with respect to y, so that's x times y. We integrate this is y to the minus 2, so we add 1 to it and divide by the new power. That makes that plus x cubed over y. And when we integrate this with respect to y, we're just going to get plus 2yz. But there could be a function that depends upon x and depends upon z, because again, if you differentiate this with respect to y, these parts will generate this, and this would vanish. And finally, and most simply, in this term, if we integrate with respect to z, we are going to obtain minus phi is 2yz plus some unknown function of x and of y. So these three equations together will tell us what phi is. So this term here and here must be part of our answer. This term here and here must be part of our answer. And the 2yz term here and here must be part of our answer. Could there be anything else that depends upon x, say? Well, no. Supposing we had something which depended upon x and just upon x, that would not be seen here, but it would have to be written here because this term only depends on y and z, and there is no other x dependence there. And in a similar way, you can convince yourself that this is the complete answer. So on this slide, what we've done is we said this is our convention for defining the vector field as minus the gradient of a scalar potential. And all we've done is we've integrated the individual coefficients, being careful about the minus sign, and in that way found phi. So here we integrated with respect to x, here we integrated with respect to y, and here we integrated with respect to z. Our solutions were only up to functions which depended on the variable that we hadn't integrated with respect to, because were we to differentiate both sides, with respect to here x, here y, and here z. These terms would all cancel. But looking at these answers, we were able to put them together and see that this is the complete solution. And with that, let's use the scalar potential on the next slide to calculate a line integral of our conservative vector field. So here is the potential that we calculated on the previous slide, and it is only defined up to an overall additive constant, because if you take the gradient of this, any constant that you add will vanish in all of the coefficients. So let's now use this to recall that the line integral across some path C for a conservative vector field is, with our convention, minus the scalar potential calculated at the end of the path minus the scalar potential calculated at the beginning of the path. And in our problem, the end of the path was at x is 4, y is 5, z is 6, and the start of the path was at x is 1, y is 2, z is 3. So what we need to do to calculate our line integral of the vector field is just to substitute these values of x, y, z into our scalar potential. So minus phi is this. So paying attention to the minus sign, minus phi is this evaluated at x is 4, y is 5, so that's 4 times 5, plus 4 cubed over 5, plus 2 times 5 times 6, and could in principle be an additive constant, but that will cancel in the difference, so we never need to write such a constant. And then we have minus phi, so that's plus phi at Ri. That means we need to have another minus sign here. And then we just substitute here. X is 1, y is 2, z is 3, and we obtain this. We just play with the numbers, tidy things up, and we get 783 over 10. This is what we have calculated. So I've just tried to draw our axes, x, y, and z. I've tried to indicate where our points are. X is 1, y is 2, z is 3. That's our starting point. And x is 4, y is 5, z is 6. That's our finishing point. And because this is a conservative vector field, it doesn't matter which exact path we take to go from here to here. It's just the starting and end points that matter. So I could have drawn a different path going from here to here, and we would have obtained the same result. So this was our formula for calculating the line integral of a conservative vector field in terms of the scalar potential, and this was an example of it. And with that, I'll stop this video.